Swayam Prabha. Digital India. Educated India.
Hello viewers, welcome to lesson 12 of module 4. As you know, module 4 is on payment design. This lesson will be about analysis of concrete payments. You may recollect that in lesson 11 we have discussed about analysis of flexible payments. Once we complete the theory that is required, the models that are required to analyze both flexible type of payment and also rigid type of payment, then we will be in a position to start discussing the design procedures, various design procedures that are existing. The specific objectives of this lesson will be, after completing this lesson, it is expected that the student would have learnt about various components of concrete payment. Unlike flexible payment, concrete payment is significantly different in the sense that it is not usually a continuous layer. It is built in terms of number of slabs connected through joints, different mechanisms. So, we need to understand the difference between how flexible payments are constructed and how concrete payments are constructed. What are the main components that are there in concrete payments. So, after completing this lesson, it is expected that the student would have known, would have understood what are the components, what is the function of each component in concrete payment. It is also expected that the student would be familiar with the common theory that is used for analysis of concrete payments, and also about the assumptions that are associated with the theory. And it is expected that the student would have some understanding of how to compute stresses using this theory, stresses associated with load and also associated with climatic and other factors. And it is also expected that the student would have understanding of how to select a critical combination of loads and climatic conditions and the associated stresses. As we have already discussed in earlier lessons, traditionally payments are divided into two categories, flexible and rigid. This categorization is mainly on the basis of how the payment materials or payment as a whole responds to load and climatic conditions. Flexible payments usually have, as we all know, bituminous surfacing over granular base, granular subbase, which in turn are placed over subgrade. There will be flexible payments without bituminous surfacing also. So, basically you will have subgrade, subbase or base, either both or one of them, and as a surfacing it may be either bituminous surfacing or it can be simply granular surfacing also. It can come in other combinations also. As far as rigid payment is concerned, it typically consists of Portland cement concrete slab with or without a granular base and both these layers placed over subgrade. Concrete payments are different from flexible payment in the sense that the deflections when they are subjected to traffic loads are very small, hence the name rigid. Of course, it is not truly rigid because they also deflect. The high flexural strength of the concrete slab is so predominant compared to the strength of the foundation that is mobilized. So, the strength of the foundation is not in fact very significant in the case of concrete pavements. It is the strength of the slab, stiffness of the slab, that is more important. But whereas in the case of flexible pavements, the strength of the foundation plays a major role in the performance of pavements. Concrete pavements are usually finite slabs with joints. You will see number of joints in a concrete slab, but you can also, these are typically called as jointed concrete pavements. But you can also have continuous pavements without joints, though not very common in India. To avoid joints, because joints are normally difficult to maintain and these are places of weakness. So, if one wants to construct pavements without any joints, it can be done, but usually they are reinforced and called as continuously reinforced concrete pavements. This is how a typical concrete pavement would look like. It will have subgrade. Subgrade, though it is shown to be of finer thickness, it will be of infinite thickness. The top portion, as you learnt earlier, will be of prepared foundation, prepared to proper specification and strength, over which you may have a granular base or sub base depending on the requirement, and over which you have a concrete slab. This is the general arrangement of a concrete pavement. Right at the bottom you will have the subgrade, above which there will be a sub base or base, this layer, over which will be placed number of panels of concrete slabs. How many panels, what size will depend upon what is the width of the pavement that is being constructed, 1 lane, 2 lane, 4 lanes. Accordingly, you may see number of lanes. The size of the slab also will be dependent on the width of the pavement that is being constructed. The other components that we see here are, as you can see here, dowel bars, in fact these are bars that connect adjacent slabs. You also see another bar here which is known as tie bar. They have different functions which we will be discussing in the subsequent slides. The longitudinal joint separates maybe the panels that are placed in different lanes, and there will be transverse joints at a selected spacing. The spacing at which the transverse joints are to be provided and the need for a longitudinal joint will be a function of various conditions. These things we will be discussing subsequently. So, in general, the concrete pavement will have subgrade, granular base, concrete slab, it will have longitudinal joints, it will also have transverse joints, and it may have dowel bars across transverse joints, it may also have tie bars across longitudinal joints at other joints also. So, as we have just seen, these are the components that a concrete pavement will have: concrete slab, granular or stabilized base. The base can be either a granular base or it can be a stabilized base, it can be dry lean concrete base, it can also have a granular sub base, which can be stabilized sub base also, and it will of course have a subgrade. Joints are the other main features of concrete pavement which significantly affect its performance. There are various types of joints. In fact, there are three main types of joints: contraction joint, construction joint, and expansion joint. Contraction joints are provided to control cracking in the slab due to shrinkage, thermal contraction, moisture or thermal variation within the slab. These are basically there to relieve the stresses that are produced because of variation in temperature, variation moisture, basically variation volume either of the slab or with reference to slab, variation volume of the foundation. These are usually provided in the transverse direction and at predetermined spacing. These would be perpendicular to the direction of travel. In some cases these are provided with some skew, not exactly perpendicular to the direction of travel. This is to avoid the critical combination of both wheel load stresses and other stresses being very critical at these junctions. They can also be provided in the longitudinal joint depending on the requirement of load transfer across and also the dimension of the slab in the lateral direction. This is a typical contraction joint. The diagram that the figure that you see in the upper portion of the sketch is a contraction joint without a dowel bar. So, this is titled as undowelled contraction joint. These are formed by making a cut in the pavement. You can see there is a cut made in this portion. So, this is cut by saw after certain time, after which the concrete is placed. Once it is cut, we have made a joint of weakness in the pavement. So, automatically after some time a crack will be initiated and will progress towards the bottom. So, you will see a full depth crack there, but what is interesting to note is usually if the two parts of the slabs are not separated from each other, there will be granular interlocking along the joint. So, it is expected that the load placed on one portion of the slab will be transferred to the other portion through this granular interlocking. So, as long as there is sufficient granular interlocking available there, the crack does not become separated, the interlock does not deteriorate, that means the material is not lost, then we can expect some amount of load transfer from one slab to the other one. Thereby the stresses are in general reduced. If these two slabs are entirely separate, there is no connection between these two, obviously any load placed on one slab will produce more stresses compared to the condition where the load is transferred to the adjacent slab. May not be fully, but some part of the load will be shared by the adjacent slab. So, in the first mechanism where there is only a saw that is cut and then you have a crack that is developing in this concrete pavement, which is undowelled contraction joint, we are depending on load transfer on the granular interlocking mechanism at this joint. The figure at the bottom shows a dowelled contraction joint. During construction, dowel bars will be placed inserted into the concrete. These are the dowel bars. Dowel bars will be inserted into the concrete, then the concrete will be completed. After that, at this location there will be this saw cut that is made. Once that saw cut is made, it will be followed by subsequently by the development of this crack. So, in this case there will be granular interlocking also. Besides this, there will also be thick dowel bars that connect both the slabs. So, load transfer will be through this granular interlocking and also through the dowel bar system that is placed. There will be number of dowel bars placed across the width of the slab. So, all these dowel bars acting as one system will be transferring load from this slab to the adjacent slab, but load will be transmitted from this slab to the adjacent slab through the granular interlocking mechanism also. The dowel bars are basically short steel bars. The diameter will be typically 30 to 40 millimeter. Length also will be about 400 to 500 millimeter length. They connect adjacent slabs. However, they do not restrict the horizontal joint movement. If the two slabs have to go separate away from each other because of contraction, that is permitted, because the dowel bar is not going to be bonded to the slab on both sides, at least on one side it is going to be smooth. So, that separation is going to be permitted. they are meant to reduce joint deflection and as a result reduce the overall stresses in the slab. These are either coated by epoxy or inserted in plastic sheath to prevent corrosion and also to break bond between the bar and the concrete. This breaking of bond allows adjacent slabs to either expand or contract independent of the movement of the slab in which the roll bars are inserted. There is another type of contraction joint. The one that is shown above is already discussed in the previous slide, which is very similar. It is untied contraction joint or it is undoubled contraction joint. Basically, there is nothing, only socket is made, which is followed by development of a crack. It is similar to what we discussed in the previous slide. But one that is shown at the bottom of this slide is a socket followed by a crack, but here what we see are tie bars inserted into the concrete while it is being placed, and these are deformed tie bars, whereas roll bars are smooth. These are deformed tie bars. So, we can easily understand the function of a tie bar. These are not very thick, the diameter will be usually be small. The main function of tie bar is to keep these two slabs together and thereby hoping that load transfer is going to be possible through granular interlocking mechanism. We are only trying to see that the two slabs do not get separated at this joint crack and thereby ensuring that the granular interlocking is still going to be available, and as a result we expect to have some load transfer mechanism available there. We are trying to see that through the by inserting these tie bars, we are trying to see that these two slabs do not get separated and there is no gap there. As I just indicated, tie bars are deformed steel bars and these are placed to hold the two adjacent slabs together. They indirectly help in the transfer of load through granular interlocking. Load transfer provided by the tie bars themselves, there are also steel bars placed across the joint, but the load transfer provided through the tie bars is usually negligible and not generally taken into account. These are normally used for longitudinal joints. There is another type of joint that is necessary, because at the end of construction, because one cannot construct a 100 km length of slab continuously, it has to start and started again. So, you have construction joints when you stop work and start again. So, construction joints are provided to separate successive construction activities. Normally what is done is that they are planned to coincide with other joints like transverse contraction joints. You can see two typical construction joint types that are normally provided: butt joint and with roll bars. So, you have this butt joint provided here, and then you have a socket made, and you also have smooth roll bars inserted at the time of placing the concrete. This is where we want the load transfer to be through roll bars, but where load transfer across the joint is not a major problem, especially for pavements where there is not much of a heavy traffic. For low volume roads, you may not provide roll bars. So, we can just keep them together by using tie bars. Okay. So, this also is a butt joint. Again, these can be provided along longitudinal joints. You can also have construction joint in the transverse direction and also in the longitudinal direction. When you have a transverse direction, normally we try to provide roll bars to connect this to the next slab. In the longitudinal direction, load transfer is not such an important consideration. So, we normally provide tie bars to connect these two slabs in the longitudinal direction. We can have another type of construction joint. Instead of making a butt joint, we can make a key joint. As you can see here, there is a key arrangement here, and this will also be complemented by insertion of deformed tie bars if it is a longitudinal joint. You can also have it for a transverse joint, then you can have dowel bars also placed across these two slabs, but since we are providing a key, normally you may not require dowel bars there, because through this key load transfer can be ensured. We also have expansion and isolation joints. In general, they are similar in their function. Expansion joint is provided at specific location to permit thermal expansion of slab without damaging the adjacent slabs or structures. Obviously, when temperature increases uniformly with reference to the temperature at which the concrete is placed, then the concrete is going to expand. The concrete should be permitted to expand, otherwise there will be significant amount of compressive stresses that are going to be generating in the concrete slab. To avoid that, normally expansion joints are going to be provided at specified spacing. Isolation joint is slightly different in the sense that these are provided to isolate the pavement from adjacent structures such as buildings, bridges, sidewalks, etc., because the concrete slab may be passing through various structures. So, it should not be pushing against those bridges or culverts, abutments. So, there is going to be joint that is going to be provided between the structure and the concrete slab. So, this is to allow independent movement of the pavement or structure without causing any damage. These are two typical types of joints that are provided. Expansion joint by definition has to be a separation, there has to be sufficient gap provided for the slab to expand and then close the gap. So, there has to be sufficient width of gap to be provided. Obviously, one has to maintain this gap by sealing it to prevent from the foundation material from coming through the joint, and also from water going into the pavement and weakening the foundation. So, this is usually sealed with some filler material, suitable filler material. If there is no load transfer mechanism between these two slabs, that means we are not providing any dowel bars, then to account for the excessive stresses that are going to be close to the joint, one can either thicken the slab near the edges, or alternately we can provide dowel bars here. As you can see here, we can provide an expansion cap here to permit the lateral movement of the slab when it is trying to expand. We are usually concerned about the load transfer mechanism available at joints, and in all the current, most of the current design procedures, the efficiency with which load can be transferred from one slab to another one is usually taken into account. So, it is very important that load applied on one slab is shared by the adjacent slab for better performance of the pavement, to reduce the overall deflections and to reduce the stresses in the slab and also on the foundation. If load transfer across slabs is poor, distresses such as faulting, pumping and corner breaks and various other problems occur. Load transfer can be attained through different mechanisms. Some of them we have already discussed, like granular interlocking, through dowel bars. The ability of the pavement to transfer load at joints is referred to as load transfer efficiency. The load transfer efficiency can be explained with these two diagrams. In the diagram that is shown above, the load that is placed on the left hand side, there is no connection between these two slabs. Obviously, the slab on the right hand side is not participating in sharing the load placed on the left hand side. So, this is a situation where there is zero load transfer efficiency. But for the same situation, same slab, assume that we have connected these two slabs by dowel bars, a system of dowel bars. It is not just one single dowel bar, it is a system of dowel bars placed at a specified spacing. So, what you see here is what is actually depicted here is the deflection on the left hand side is almost equal to the deflection on the right hand side. This means that there is almost 100% load transfer efficiency. That means both the slabs are sharing the load in equal amount. That means the joint is able to transfer. It is almost like a monolithic construction, as if the slab was just extending at that joint. We can also expect load transfer through granular interlocking also, if you just provide only tie bars. So, this is a situation where we have crack developing through the slab, and we have provided tie bars to ensure that the slabs do not get separated. This is one type of load transfer mechanism. Another mechanism is you can also have cracking, granular interlocking. You can also have dowel bars. So, both granular interlocking and dowel bars together provide this load transfer mechanism. The load transfer at joints, as I just discussed, can be through granular interlocking. It is expected along the cracks that form at the transverse joint, which develop below the socket. For low volume roads, adequate load transfer can be expected to be provided by interlocking. Usually we do not provide dowel bars in the case of very low volume roads. So, we assume that the granular interlocking mechanism that is going to be developing is capable of providing sufficient load transfer efficiency to keep the stresses within permissible limits. So, normally low volume roads we do not provide dowel bars. For higher traffic volumes and thick slabs, obviously dowel bars are going to be necessary. Coming to the analysis of stresses in concrete slabs. Stresses in concrete slabs are usually produced due to various reasons. The number one reason is stresses that are produced because of application of wheel loads. Obviously, these are going to be flexural stresses because they make the slab to deflect and bend. What is to be noted is it is not just one single application that we are concerned about. Of course, when the pavement is subjected to one very heavy load, that itself may be sufficient to cause failure of the slab. But we are also concerned that especially in the case of highway pavements, there are going to be a large number of repetitions of pavements, loads to be applied, especially if we are considering a period of 10 to 15 years. The number of loads that are going to be applied in terms of commercial vehicles or in terms of axles can be several millions. So, we have to understand that millions of loads are going to be applied if we are talking about highway pavements or any other pavement also. There are going to be repetition of loads of different magnitudes. So, all of them are going to be producing some amount of damage, small or large. There are going to be stresses that are going to be produced because of temperature differential within the thickness of the slab. Because if there is temperature differential within the slab, that means top temperature is more than bottom temperature or bottom temperature being more than top temperature. So, slab either curls up or curls down. This also can produce stresses in the slab. We will discuss how to calculate that, what type of stresses are produced. Another reason for stresses that being produced in concrete slabs are if the temperature increases uniformly. For example, when the slab was placed, there is certain temperature. Afterwards, temperature is either increasing or decreasing. We are not talking about daily variation of temperature. Morning time, daytime being hotter at top and then cooler being at bottom, and night time being cooler at top and then hotter at bottom. We are not talking about that. Season to season, during one season temperature is going to be, let us say, 10 degrees centigrade. Another season the temperature could be 50-60 degrees centigrade. So, accordingly there is going to be uniform expansion or contraction. If this uniform expansion and contraction is restrained, if it is not restrained, there will not be any stresses. Only when this expansion or contraction is restrained, there are going to be stresses that are going to be produced. So, depending on the degree of restraint that is going to be provided to the expansion or contraction, the corresponding stresses are going to be generated. So, there are going to be stresses because of wheel loads that are applied, there are going to be stresses because of variation in temperature within the thickness of the slab, because it is going to be either trying to curl up or curl down, or there is going to be stresses that are going to be produced if restraint is provided to uniform expansion and or contraction of the slab. There can also be stresses if there is change in moisture and corresponding volume change either in subgrade or in base or in slab. If any one of these components undergo volumetric change, and if that is restrained by the other components, for example, slab is trying to undergo volumetric change, foundation is restraining that, or foundation is trying to undergo volumetric change because of variation in moisture content, but slab is trying to prevent that. So, there are going to be stresses generated in both the components. Normally, what we have to consider is a critical combination of all these stresses produced by various factors. For analyzing concrete pavements, we should be able to analyze these pavements and then find out if a load is placed, load of certain magnitude of certain configuration is placed on the slab of certain type, strength, what will be the wheel load stress. Also, if there is so much of variation of temperature within the slab, what will be the corresponding stress. Although if there is uniform variation of temperature, what is going to be stress, we should be able to calculate that. So, we have to have a mechanical model or theoretical model using which we will be able to analyze the pavement. There are two commonly used models for concrete pavements. These two differ in terms of their assumption about foundation. What I am talking about here are simple theoretical models that are available. There are lots of variations that are currently practiced to these simple models. More complex models are available, but I am going to only discuss about those simple models that are in practice. So, as I said, the main variation is in terms of the foundation and the assumption made about the foundation. We either assume the foundation to be as dense liquid or spring or Winkler foundation, they all mean the same thing. That means the foundation consists of number of springs. Alternately, we can assume it to be elastic foundation. This slide here shows the two types of foundation. On the left hand side, you have slab placed on a spring foundation or Winkler foundation or dense liquid foundation. This is the most commonly used foundation type for analysis of concrete pavements. It assumes no shear strength for the foundation, and these are usually suitable for soft cohesive soils. On the right hand side, the foundation that is considered is an elastic layer, a combination of elastic layers. So, here is a slab placed on number of elastic layers, usually it is subgrade and base or only the subgrade. This analysis is slightly more complex compared to the analysis that we make for slab over spring foundation, but this is usually suitable for concrete pavements with stiff base or stiff foundation. As I said, spring foundation is the most common assumption that we make about foundation of concrete pavements. In this, the foundation is represented by its spring constant known as modulus of subgrade reaction, K. K is normally determined, if this is being determined from a field test, it is determined by conducting a plate load test on the foundation. There is a parameter that we normally use to represent the relative stiffness of the slab and the subgrade. Slab will have one stiffness, foundation will have different stiffness. To have an index which represents the relative stiffness of slab with reference to the subgrade, we use the term called as radius of relative stiffness. The assumption using which the radius of relative stiffness is adopted is, when the slab deflects, the pressure that is produced at different locations is proportional to the deflection at that location. So, the reactive pressure is proportional to the deflection. So, K is the proportionality constant, which we called as modulus of subgrade reaction. So, the radius of relative stiffness of slab and subgrade is given by comparing the stiffness term of the slab and a similar term that we use for the foundation. The stiffness term for slab can be given as EHQ, where E is the modulus value of concrete, H is the thickness of the slab, divided by 12 into 1 minus mu square, where mu is the Poisson ratio value of the concrete. Equating this to K, where K is the modulus of subgrade reaction, and L to the power 4, where L is the term that was just coined, radius of relative stiffness. Equating these two, L can be expressed in terms of E, H, K and mu by the expression given here. So, this is L, radius of relative stiffness of slab and subgrade, given as a function of modulus value of concrete, thickness of concrete, modulus of subgrade reaction of foundation, and then Poisson ratio value of concrete. Determination of modulus of subgrade reaction can be done by conducting a plate load test. Plate load test we have briefly discussed when we were discussing about material characterization. In this, we apply load in an incremental manner. We use a stiff plate, a series of plates used to stiffen the loading plate. This is the rigid plate. So, we apply incremental load and measure the deflection, surface deflection of the pavement, and then plot the load versus deflection diagram. Like this, and the slope of this diagram at a specified deflection is taken as modulus of subgrade reaction. Normally, we use 750 millimeter dia plate to conduct plate load test, and we also have to normally make corrections for moisture. We normally use a K value corresponding to weakest condition in designing pavements, but if you conduct this plate load test at a different point of time where the foundation is not in its weakest condition, so we normally have to make some correction corresponding to the weakest condition. The K value is determined corresponding to 1.25 millimeters. When we analyze pavements, we use basically most of these agents use Westergaard's analysis, either in its original form or in the modified form, because Westergaard has given several expressions for computing stresses in different critical regions of slab. Some agencies have directly adopted those expressions, but many agencies over time have gradually modified the Westergaard's expressions so that the computed values correlate with the values that have been measured during field experiments or laboratory experiments. Westergaard's analysis assumes that slab is placed on a Winkler foundation. We have just described Winkler foundation, which is comprising of springs. Westergaard's analysis typically gives expressions for computing stresses in the slab in 3 different regions. These are considered to be critical regions. One is corner, edge region and interior region. As you can see here, corner, interior and edge region of the slab. Of course, if you have suitable programs that are available, you can calculate stresses and strains deflections at any point on the slab, but typically solutions are available for corner, edge and interior regions of the slab. Closed form solutions are available given by Westergaard's for single wheel load, circular contact area or semicircular contact area or semi-elliptical contact area, but circular contact area is the most commonly used shape of load contact. Number of influence charts are also available, Pickett and Ray, providing solutions for multiple wheel loads of different configurations. As we know, the load contact area is not in general circular in shape. So, using influence charts, we can determine the stresses due to multiple wheel loads and wheel loads having different contact areas. Both the types of solutions, either Westergaard's analysis or influence charts developed by Pickett and Ray for multiple wheel loads, are normally applicable for large slabs placed on liquid foundation or spring foundation or Winkler foundation, or foundation being in elastic layer. There are a number of finite element programs that are also available at present, which are capable of solving the payment systems for multiple wheel loads, for different types of load transfer mechanisms. The two types of solutions that are available in the form of closed form solution and in the form of influence charts are not normally capable of handling load transfer mechanisms, different types of load transfer mechanism, and also finite element programs can handle different types of foundations and different interfaces between slab and foundation, rough interface or smooth interface. So, all these complex situations cannot be solved by standard closed form solutions. So, nowadays most of these agencies normally use finite element programs to solve these complex situations, where you have different types of interfaces, different types of foundations are to be modeled, and different load transfer mechanism is there. So, to be able to solve all these problems, normally nowadays finite element solutions are being adopted. But we will confine our discussions to Westergaard's solutions of wheel load stresses. Obviously, all the assumptions that go with Westergaard's solutions will have to be taken together. Westergaard in 1926 developed equations for solution of load stresses, as I mentioned, at three different critical regions of the slab: interior, corner and edge. Interior, the load is placed in the interior and away from all the edges. That is the definition of what is an interior region. The load has to be sufficiently away from all the edges, whereas edge is the load placed. Edge loading is, this is a situation where the load is placed along the edge away from the corners. On the other hand, corner loading condition is defined by load being located on the bisector of the corner angle. Again, this diagram depicts the three critical regions: edge, corner and the interior region. These are the expressions given by Westergaard's for a Poisson ratio value of 0.15 assumed for concrete, for load being placed in different regions: interior loading, edge loading and corner loading. For example, interior loading case, obviously there will be tensile stresses at the slab bottom and then compressive stress at the top. So, sigma interior in terms of PSI. So, we have to understand that these equations are in FPS system. So, sigma in terms of PSI is given as a function of single wheel load that is applied, P. So, this is the wheel load that is applied, this is a single wheel load, P, thickness of the slab, H, L is the radius of relative stiffness, we have discussed a few slides back, and B is a parameter I will just discuss. So, this is a function of load that is applied and the thickness of the slab, and L and another parameter B. L we know is a function of E, H, K and Poisson ratio. Similarly, edge loading, the expression that is given is also in terms of wheel load, thickness, L and B. So, we also have the expression for corner loading here. P, as I have indicated, is the wheel load in pounds, H is the slab thickness in inches, A is the radius of wheel contact area, assuming circular contact area. If you know the wheel load and if you also know the contact pressure, we can calculate the radius of load contact area, assuming circular contact area. B is termed as radius of resisting section, again in inches, given as 1.6 times a square plus h square, h is the thickness of the slab, under root minus 0.675 into thickness of slab for the condition where a is less than 1.724 times thickness of slab. If a is greater than or equal to 1.724 times thickness of slab, then b is taken to be equal to a. L, of course, as we already defined, is the radius of relative stiffness in inches. We also have expressions for computing deflection due to wheel loads. Many times we are also concerned about the magnitude of the deflection, because this is very critical at locations where we have joints. If the slab deflects too much, the foundation below is going to be damaged and the slab is going to lose support at the joints. So, a lot of large deflections at the joints are going to be damaging the foundation, because that foundation is going to be gradually be eroded, the material is going to be lost. So, that will lead to loss of support at these joints. So, we are concerned about large deflections occurring in the slab also. So, these are the three expressions that we have for corner loading, interior loading and edge loading and the corresponding deflections. As in the case of stresses, here also these three deflections are a function of load that is applied, K, L that is radius of relative stiffness, and A that is radius of load contact area. There are a number of influence charts that are available, developed by Pickett and Ray based on Westergaard's theory. This is for a Poisson ratio value of 0.15. This is an influence chart developed for computing the movement in the interior region. This diagram, this is a typical representation of the influence chart. So, these four blocks that I have represented here are the wheel loads. Here I am depicting the wheel contact areas to be rectangular in shape, or I can draw any other diagram, but these wheel load imprints have to be drawn to a proper scale. That what is the scale to be used is represented by this line that is drawn here. So, on these influence diagrams you will see a line. So, if you can measure that length, that corresponds to L, which is radius of relative stiffness. So, for the given slab, if you know the properties of E, H, Poisson ratio and K value, we can calculate the value of L in inches. So, that is the length that has been drawn. So, this line here corresponds to the L value that is calculated for the given slab. So, once we identified what is the scale to which the imprints are to be drawn, that means this length of this line should correspond to value of L. Then to the same scale we can draw the imprints. What we have to do is count the number of blocks that are there within these tire imprints and count the blocks that are there within all the wheel loads that we place on the influence chart. That is the number that we have in this expression, where the movement in the interior region is a function of, this is the contact pressure P, L is the radius or relative stiffness, N is the number of blocks occupied by all the tire imprints, then this is the moment that you get. Once you get the moment, we can compute the flexural stress using this expression. So, depending on the position of the wheel loads, the number of blocks that these occupy will also be varying. We have a similar influence chart for computing deflection in the interior loading. Again, here also we have to place the tire imprints on the diagram, draw them to the same scale given by the represented by the line that is there at the top, count the number of blocks N, and then contact pressure, radius or relative stiffness, and a parameter D, which is known as modulus of rigidity, computed as EH cube by 12 into 1 minus mu square. So, if you know the properties of the materials to be used, we can compute the modulus of rigidity. We should also of course know the thickness of the slab. So, using these influence charts, we can either compute. Similarly, there are other types of influence charts available to compute other parameters. we can compute stresses or deflections in different locations for multiple wheel loads and also for wheel loads of different contact areas. There are also going to be stresses due to friction. This we have discussed earlier. Friction will be mobilized when the slab is trying to move. Okay. So, friction between slab and foundation causes tensile stresses in the slab, that is when it is trying to contract. For plain cement concrete, the spacing of contraction joint influences the friction stresses. Longer joint spacing may be required for reinforcing steel to take care of the frictional stresses. Tie bar spacing also depends on the frictional stresses. Let us understand why there will be stresses in the slab because of friction. Volumetric change in concrete induces tensile stresses in concrete. We are referring to a case where it is trying to contract. This would also cause opening of joints leading to reduction in load transfer efficiency. When a slab tries to contract, the outermost part moves the maximum, the central part of the slab moves the least. So, the friction that is mobilized towards the end of the slab is going to be more, towards the center of the slab almost zero friction is mobilized. So, this is how it is going to vary. The friction that is mobilized from the end to the center of the slab, this is how it is going to vary. But what we normally do is we try to get an average value of friction that is going to be mobilized, and that is the value that we are going to use in the analysis of these slabs. These slabs tend to move from both ends towards the center. Foundation prevents it from moving, leading to frictional stresses. The restraint provided by the foundation to the movement of the slab, that is the reason why stresses are going to be caused. Main reason is that either the slab is trying to move or the foundation is trying to move. So, one is restraining the other one. Normally, we are concerned about the contraction of the slab because of reduction in temperature, that being restrained by the foundation. So, the friction is mobilized there, the corresponding stresses are going to be generated in the slab. So, this can easily be calculated. The friction mobilized depends on the relative moment, 0 at center and maximum at some distance from center. Average friction has to be assumed Fa. So, assuming that we have, if W is the unit weight of concrete, L by 2 is the portion of slab that we are considering, H is the thickness, 1 is the width, and Fa is the average coefficient of friction, then this is the stress that is generated and this is the thickness and this is the cross sectional area. Okay. So, this corresponding stress can be computed using this expression. We can provide longitudinal or transverse reinforcement and tie bars across longitudinal joints to handle these stresses. The area of reinforcement to be provided is given by this expression, where B is the width of the panel and Fs is the allowable stress. As I indicated earlier, there are going to be stresses within the slab due to temperature difference also. Due to temperature differential within the slab, during daytime the slab tries to curl up, top will be convex. During night time the slab curls down, top will be concave. Due to weight of the slab and the resistance offered by the foundation, stresses are going to be induced. The slab will not be fully be permitted to either curl up or curl down. There is restraint provided by the self weight and also by the foundation. So, there are going to be stresses getting developed. During daytime, the self weight is going to pull it down. So, there will be tension at the bottom, compression at the top, because there is going to be more temperature at top compared to the temperature at bottom. Whereas, on the other hand, during night time, the temperature at the top fiber of the slab is going to be more compared to the bottom fiber. So, the slab is going to be pulling this down. So, there is going to be compression at bottom and then tension at top. So, these curling stresses can be computed using these expressions. Sigma x as a function of modulus value of concrete, alpha is the coefficient of thermal expansion, delta T is the temperature differential that is there from top to bottom. There are coefficients like Cx and Cy that we have to determine because the slab is finite. So, depending on the dimensions of the slab, Lx and Ly we have to determine two coefficients Cx and Cy, then we can determine the stress in sigma x and then sigma y. What we need other information is modulus value of concrete, alpha is the coefficient of thermal expansion of concrete, and the temperature differential. We need to find out what is sigma x and sigma y. Once you get those two parameters, we can compute the stresses arising out of curling. Bradbury has given coefficients to find out what is the value of sigma x and sigma y depending on the dimension of the slab with reference to the radius of relative stiffness. If you know the dimension of slab, for example Lx by L, then we can find out what is the corresponding coefficient, that is Cx. Using this expression, coefficient C multiplied by elastic modulus value, coefficient of thermal expansion, temperature gradient by 2. In the corner region, the curling stress is normally negligible because the restraint provided by sulphate is almost negligible there. The critical combination of load and curling stresses that is to be considered. In the case of night time, the curling stress compensates the load stress because curling stress tension will be there at top and load stress compression will be there at top. On the other hand, noon time the curling stress will be additive to load stress, hence this is the critical combination. Let us take a few questions from this lesson. Answers to this will be provided in the next class. What is the main difference between flexible pavements and rigid pavements? What is the function of contraction and expansion joints in concrete pavement? What is the function of dowel bars and tie bars? What is the most commonly used parameter to characterize foundation for analysis of concrete pavements? How is it obtained? Why do thermal stresses occur in concrete pavements? Now we will have answers for the questions that we asked in lesson 411. What are the three main characteristics considered for selecting an appropriate model for materials? The three main characteristics are the relationship between stress and strain, whether it is linear or non-linear, the response of material after applied load is released, whether it is instantaneously elastic, complete recovery over time, or partly not recovered, some is recovered. So accordingly terms such as elastic, plastic, viscoelastic, various combinations of terms can be used to describe the material. The third characteristic is the time dependent behavior of the material. Accordingly it is either viscous or non-viscous. Within viscous also it can be linear, non-linear depending on the relationship between time and the deformation. It can be linear or non-linear. Explain how to estimate the elastic modulus value of a single layer system by conducting a plate load test on the pavement. This we have already discussed earlier. If you conduct a plate load test, measure the surface deflection, know the value of contact pressure P, radius of load contact area A is known, P is known, A is known. So we know the expression for a rigid plate, surface deflection is equal to 1.18 Pa by E, where E is the modulus of separate. P is known, A is known, deflection is measured, we can estimate the modulus value. What are the main assumptions associated with linear elastic layered system? Linear elastic layered system, we assume it is comprised of number of layers. Each layer is characterized by its thickness, elastic modulus value, Poisson ratio value. All the n-1 layers are infinite in horizontal extent, last layer is infinite in both the directions. Solve the problem given in the next slide. I am not reading out the problem completely to save time, but I will discuss the solution. What is given is we have to find out the thickness of the granular base so that the surface deflection under the action of 20 kN load will be less than 0.2 millimeters. The given is plate load test is conducted on subgrade. As we just discussed, we can find out the modulus value of the subgrade because deflection is known, P is known, A is known, we can find out the subgrade modulus value. Then granular thickness of known thickness is built over this. Plate load test is conducted on a two-layer system. So for a rigid plate, this is the expression for surface deflection. P is known, A is known, surface deflection is also known, E subgrade is also known. We can find out F2 from this plot. So once we know F2, from F2 and from known thickness we can obtain the ratio of E1 by E2. Next we have to find out what is the thickness of the layer to be provided. So we know the subgrade modulus value. The allowable deflection is 0.2. This is a flexible plate. So 1.5 Pa by E subgrade into F2. So F2 has to be obtained. E subgrade is known, P is known, A is known, surface deflection is known. So once we obtain F2, we can get H1 by A from known F2 and E1 by E2. Then we can find out H1.